Dear students, good morning. Let us resume back our video lectures on machine learning for image processing. In this video lecture, let us continue our discussion on principal component analysis. We have seen in the previous video lecture how to represent the samples of higher dimensions by their projections onto the principal components. We have seen how the principal components essentially are oriented towards the directions of maximum scatter of data. We have also seen capturing few of such principal components. We can effectively represent even higher dimensional, very high dimensional data samples. In this lecture, let us quantify how much is the error if we consider projecting onto the single dimension or multiple dimensions or to the large number of dimensions. So we will see how many dimensions are appropriate for projecting a given data samples when we consider principal component analysis. Let us also see the other applications of principal component analysis or principal components. Let us resume back to our discussion. Hope you are able to see the screen. We have seen in the previous lecture that if we want to project onto a particular direction, the direction of projection is given by the eigenvector or the dominant eigenvector of the scatter matrix. If S is the scatter matrix of all samples and lambda max is the maximum eigenvalue of the scatter matrix, and this corresponding eigenvector to this lambda max and S is the direction in which we should project the data to capture most of the information of the data when we wish to project the data onto a single dimension. And hence, the given samples will have an alternative representation in terms of AK, and the reconstruction of these projected lengths or projected samples can be done effectively using E and M through the expression given here, right? Then subsequently, we have discussed that if we want to project on not to a single dimension, when the input dimensionality is very high, we can consider projecting onto D dash dimensions, and the D dash dimensions that we consider projecting are obtained by corresponding eigenvectors of after sorting the eigenvalues of the scatter matrix. So if the first maximum of among the eigenvalues of scatter matrix is lambda max 1, second maximum is lambda max 2, third maximum is lambda max 3, the corresponding eigenvectors E1, E2, E3 are considered for projecting the data. Similarly, when we want to consider to D dash dimensions, we consider first eigenvectors corresponding to top D dash eigenvalues for projecting the data. And we have seen a compact representation of the principal component vector now, because we are projecting onto more dimensions as this. Let us take forward from here to see how much should be the D dash. Should D dash be same in all cases, or should D dash be equal to D? Okay, how do we decide on the D dash or the number of dimensions to be projected for a given data? So let us see this from here, this expression. As we discussed, this is a D dash cross D matrix, and this may be represented as A transpose. Okay, where A is D cross D dash matrix, considering the eigenvectors E1, eigenvectors E1 as a column, first column, E2 as second column, and so on, ED dash as AD dash as the last column of matrix here. Okay, A transpose XK minus M. Fine. So this is a compact representation for the obtaining the principal components from the eigenvectors and the of the scatter matrix and the sample. Fine. So now let us see in an say extreme case, if we consider d dash to be equal to d, what will happen? So assume that we have seen in the previous expression that yk is equal to A transpose xk minus m, where A transpose is written as E1 transpose, E2 transpose, and so on, E d dash transpose into xk minus m. Right? Now, what we are saying is, we consider now lambda 1, lambda max 1, lambda max 2, and so on up to lambda loss lambda. Okay, mean. Right? And corresponding eigenvectors E1, E2, and so on up to ED. If we consider all the eigenvectors for projection, then yk is A transpose into xk minus m. Fine. And this ak now, this A is equal to, let me write A directly, E1 as a column vector, E2 and ED. This is D cross D, where each EI is D cross 1 column vectors. Okay, so this is a D cross D matrix. See, what is this? What is happening here? These are given samples. And yk is principal component. Vector. So, what is the difference between xk samples and the yks? Let us see that. It will help us to understand the role of principal component analysis. See, if we consider to understand the difference between the samples xk and the principal components yk, what we will see are their statistical properties. So let us see the covariance matrix and the mean values of these samples xk, and this is in some sense a linear transformation that is applied to the samples xk. Okay, transformed to yk, transformed by whom? By principal component analysis. Okay, by the method of principal component analysis. So let us see the statistical properties here. S is the scatter matrix, where sigma xk minus m into xk minus m transpose is the scatter matrix this side. Let us see the scatter matrix in this side. See, I want to find out the covariance matrix of y. First, let me write the covariance matrix of y. Yk minus mean of y, okay, into yk minus mean of y whole transpose. This is how we define the covariance matrix. Okay, because we will see the expression, but by definition, this is what is the covariance matrix of y. So I will write here scatter matrix of y. Okay, since we have now two things, I am differentiating with, okay, Sx and Sy. Scatter matrix of x and scatter matrix of y. Okay, so let us see now. What is mu y? What is mu y? See, this is expectation of A transpose, essentially expectation of yk. Okay, so A transpose into xk minus m. Where does this A transpose into xk minus 1 m has come? Because by definition, this is equal to expectation of yk. Okay, that's what I have written this side. This is equal to A transpose being a constant. I can bring this out. And expectation of xk minus m. What this m is? This m is mean of xk samples. So expectation of xk minus m is equal to what? Is equal to 0. Right? So mu y is equal to 0. Because if you take the expectation inside, expectation of sk is mean again. Okay, and mean minus mean, expectation of mean is mean itself, a constant. So it is 0. So mu, essentially this indicates that mu y, vector mu y is equal to 0. Okay, it's a zeros of d cross 1 dimension, because here we have considered the full all the directions 1 to d to present the samples. So now given this, what we want to see is mu y sy. Now I can rewrite it as expectation of yk into yk transpose. Right? So let us see this now. Let us see this. How does this simplify? Expectation of yk into yk transpose. Right? What is yk? Yk is equal to A transpose xk minus m. Please note that m means here mx. Okay, I'm right explicitly m means mx. Okay, right. So sorry, we are using the subscripts and superscripts now and then interchangingly. Okay, so now let us try to expand this. How does this expand? Expectation of A transpose xk minus m into, what should I do now? Y transpose. That is equal to xk minus m into A transpose xk minus m transpose into A transpose is A. Now I can take the expectation inside, A transpose outside, because A is a constant, sk minus m into sk minus m whole transpose into A. Now I can take A this side also out, because it being a constant matrix, right? So now this is essentially what? So the covariance matrix, I am writing the covariance matrix. It's not in fact a scatter matrix, because I have not considered a this is a statistical average. So essentially what we are writing is covariance matrix rather than a statistical scatter matrix. Okay, but they are directly related by constant, so we will not differentiate too much between them. Okay, so the covariance matrix of y is equal to A transpose. What is this? This essentially is sigma x, covariance matrix of x. Okay, into A, right? So now covariance matrix of x. Do you know? See, I want to simplify this further. What is matrix A? I know that matrix A is nothing but the matrix of eigenvalues of x, xk. Okay, so I know that matrix A is equal to E1, E2, and so on up to ED. Okay, so now I want to rewrite this sigma x, covariance matrix of xk, in terms of eigenvalues and eigenvectors. So if you are aware of eigen decomposition, if any of the real symmetric matrix can be decomposed in terms of its eigenvalues and eigenvectors as the product of eigenvalue matrix into eigenvector matrix into the eigenvalues into the A transpose, that is eigenvalue matrix transpose, eigenvector matrix transpose, where lambda is the eigenvalues put at the diagonal. Okay, big zero means all those non-diagonal elements being zero. Okay, so this is a through diagonalization procedure or writing in eigenvalues, expressing in terms of eigenvalues and eigenvectors. Okay, a given matrix. Now, making use of this, I have sigma y is equal to A transpose into, here sigma x is equal to A into lambda times A transpose into A. So what is this A transpose A? And what is this A transpose A here? This essentially is equal to, you can see here. So E transpose, essentially it will become an identity matrix because each of the eigenvectors are orthogonal. Okay, for a real symmetric matrix. Sigma x being real and symmetric. EI are all orthogonal. Orthonormal here. Okay, since we consider them as unit vectors as well. So, and hence, this essentially is equal to identity, and this is also an identity. And hence, what essentially this E sigma y is equal to now, given this, it is equal to just lambda. That's equal to lambda 1 to lambda d. Okay. More clearly, if you want to write this lambda max 1, because we have already arranged these, okay, the principal components in such a way that the eigenvector, first eigenvector corresponds to, okay, lambda max 1, okay, and this corresponds to lambda max 2, and so on. So, and hence the matrix essentially is lambda max 1, lambda max 2, and so on up to lambda min. And these are all zeros. Okay. So what are we doing through principal component analysis? What are we doing? We are essentially making a matrix transformation. We are transforming the original samples xk to a principal components yk. The advantage of this doing this is the covariance matrix of these yk samples is diagonal, in the sense that each of the features of yk are not correlated. Okay, so each of the after transformation through principal component analysis, each of the dimensions of this feature vector yk are not correlated, right? Whereas xk, in xk, each of the dimensions of the features may be correlated. Okay, so it's diagonal, uncorrelated. So yk are now essentially yk are uncorrelated random variables. Okay, sorry, uncorrelated random vector. I give any of the yk, if you see, their features are not correlated across y. So if we see now more explicitly, xk if we consider as x1, x2, and so on up to xd, and then yk if you consider it as y1, yd. Okay, so x1k, xk1, comma xk2, comma xkd may be correlated. What does it mean? If I measure for a sample, okay, assume that I measure, okay, the initial feature vector as length, okay, width, okay, lightness, and few other attributes of a given sample in a classification, or either fish or face classification or whatever, some object classification. These may be these features. Next K, okay, it's also referred to as input space, or correlated, or can be correlated, may be correlated. Okay, whereas, however, what will happen? After application of PCA, using the eigenvalues and eigenvectors of the scatter matrix of SK, this essential linear transformation makes these principal components vector, okay, yk has features, okay, y1k are not correlated. Or uncorrelated. That is, see, y1k has an information that complement to y2k, and y2k has an information complement to y3k, okay, and so on. Each of them have a complementary information. That is the reason why the dimensionality reduction here, okay, is feasible. Or see, instead of now, let us resume back to our discussion. So let us consider only detached dimensions. To represent samples xk. Okay, then what will happen here? So yk here is equal to A transpose. This A is now D dash A is D cross D dash, and A transpose is D dash cross D into xk minus m. And hence this is D dash cross 1. So here we are not considering all the directions to represent. And we are considering only the dominant directions, 2, 3 or whatever. Okay. And these dominant directions will represent the whole information of the data, because each of them has a complementary information, unlike in x1 to x3 or xk. Okay. So this y1, y2, y3 have a complementary information compared to x1, x2, xn for any of the given samples. Okay. So these features are uncorrelated, and hence the information content is maximum in y1, next in y2, next in y3, and it is almost minimal or negligible in the other components. Okay. So now how to decide on D dash? Let us see a small analogy. See here, let us see the reconstruction error. So in the previous discussion, we have seen that the reconstruction error can be quantified as xk minus xk hat. Fine. See here xk hat is defined as m plus ak into E1. Okay, when we consider only one component. Now let us see, if we consider more components, how do we write this reconstruction? Sk hat is equal to m plus ak1. Okay, I have used this ak comma 1 previously as subscript. E1 plus ak2, second principal component, into E2 and so on up to a k d dash dimensions into e d dash. Fine, I have used here e d dash dimensions. So previously when we consider only 2, this is what is the reconstructed sample. When we consider next eigen vector as well, the corresponding length, projection length I use here, and then this also helps in reconstructing better reconstruction of the sample. So it increases the reconstruction accuracy. And then taking next component and next component, so on up to d dash components will enable us to improve the accuracies gradually. Now, if I consider d dash being d, what will happen? So d dash equal to d, assume that. Then what will happen to xk hat? It will be exactly equal to xk. That means since I consider all the directions, okay, all the d dash d dash being d considers all the dimensions of the sample. It is essentially representing the sample instead of x, y, say instead of Cartesian coordinates, okay, ex, ey, okay, representing it the samples in terms of, okay, 2 different other coordinate system, that is e1 and e2. Okay, essentially it is a change of basis if you are aware about the linear algebra or representation of vector in spaces. Okay, so now this has a 0 error. Okay, so now let us see if we consider this x cat only d dash dimensions, how does this vary? Let us see that. If we consider all directions as discussed here, the error is 0. But however, when we consider only limited number of dimensions or directions to project the data, then let us see how much is the error. Let us quantify the error with a statistical estimate, since we are now considering the covariance matrix of xk and yk, and we have seen their the difference in the properties. Let us write xk hat explicitly as sigma e a k comma j, okay, and is a where j equal to 1 to d dash. Okay, this is the expression for when we project onto d dash dimensions. We have seen that d dash equal to d means error is 0. However, when d dash is not equal to d, how do we quantify error? Is considering the, as I said, the statistical approximation of the error, that is as variance of the project when the reconstructed sample when considering all d dimensions, okay, versus the variance of the samples when we consider projecting onto only d dash dimensions. Okay, please note that this indicates that I am considering the xk hat, okay, when projected when considering all d dash dimensions. So let me write here itself, okay, as a subscript here itself as d, okay, and this is d dash. Okay, so now what essentially I'm doing is in the first case I'm considering projecting onto all d dimensions. In the second case we consider to project onto only d dash dimensions. See, variance what we have seen here is the this I can rewrite it as xk minus m is equal to, let us write in matrix form to understand the relation between xk hat and e and a case. sk hat minus m equal to v1 up to vd. Let us consider first writing sk hat when all directions are considered into ak1, okay, to ak matrix A into matrix yk. Fine. We are considering all d directions. Fine. So now we have seen that the variance if you want to calculate, first let us see the covariance matrix of yd. Okay, when considering all dimensions, it is essentially equal to, as you have seen, this yd can be rewritten as A transpose into sk minus m. This is exactly the same which we have considered. Only thing now change this. We are considering all dimensions to project at one time. Okay. We are considering only few directions to project at other time. So now this is equal to lambda 1, lambda 2 up to lambda d. All eigenvalues will come into picture. Whereas with the similar lines, if we consider only d dash dimensions now, sigma yd dash has the covariance matrix, because please note that sigma yd is a d cross d matrix, whereas sigma yd dash is d dash cross d dash matrix. Okay, with lambda 1 to lambda d dash. Okay, however, when we see the variance of xd dash x, please note that here xd and xd dash are of same dimensions, because the reconstructed samples will be of same dimensions. And the essential variance here, if we see, variance in yd, okay, can be quantified as sum of all diagonal elements, that is lambda 1 plus lambda 2 up to lambda d. Here variance of yd dash is equal to lambda 1 plus lambda 2 up to lambda d dash. Okay, we can approximate the variance of x hat d using the variance of y, because we can consider this anyway d meaning, and then this is the eigenvector matrix. So approximating this with respect to the variance y d minus variance of y d dash, we can write this as lambda I equal to 1 to d minus sigma I equal to 1 to d dash lambda. So this essentially boils down to the error j, writing this as summation I equal to d dash plus 1 to d lambda. That means if I reconstruct the sample using only d dash dimensions, if x is equal to 1 to n are represented only with yk, equal to 1 to n, having this being d cross 1 and this being d cross d dash plus 1, considering only e1 to e d dash eigenvector, okay, for representing, the error in reconstruction is equal to the lambda d dash plus 1, that is lambda d dash plus 2, and so on up to lambda d. That is the left out sum of left out eigenvalues, right? Essentially, if we are representing an information in the dominant direction, in the dominant d dash dominant directions, the error is captured in the left out directions and that is effectively quantified by the corresponding eigenvalues. Okay, so this is a simplified expression for quantifying the error. Okay, fine. So if, as an example, if I give you a covariance matrix sigma x, some covariance matrix, and then if I give you also the eigenvalues of this covariance matrix, sigma x is given, and eigenvalues lambda 1, lambda 2, and lambda 3, okay, are also given. Let this be 3 cross 3 matrix, and lambda 1 equal to, they are also sorted in descending order, 3, 0.2, and 0.2. See, if you are asked to find out, you onto some dimensions capturing 90% of the information. The question here is, how many dimensions should we consider? Okay, transformation has to retain 90% of the information. See, how do we quantify the percentage of information that is retained? How do we quantify is the that is retained is equal to, since the error is given by left out eigenvalues, the percentage of retained information is given by the eigenvalues that is considered for projection. And the ratio of total eigenvalues to the considered eigenvalues will give us the percentage of information. Or the percentage of error, okay, in projection is given by the left out eigenvalues by lambda. Okay, so this is the percentage of error as exactly given by J, okay, proportional to J, and the percentage of information that is retained is this. Okay, so now given this, so how many dimensions should I consider? Should I consider only one dimension to project, or 2 dimensions to project, or 3? Okay, so how do we, let us calculate percentage information if I project onto a single dimension, that is first eigenvalue I consider. So the scatter in that first eigenvalue is accounted for, but the second and third eigenvalues are not considered. So the scatter in that dimensions are not considered. So if this is 50.2, then let us see if this is close to 90. If this is greater than 90, okay, it means that it is enough to consider. It is enough to consider the first eigenvalue itself. Okay, no need to consider the next 2 eigenvalues. Okay, so it appears that this is greater than 90, and hence we can consider this is roughly equal to this close to, okay, 99.6%. So it captures this projection, okay, by first principal component analysis itself captures 99.6% of information. So let us see in another example. Okay, where sigma x has eigenvalues, sigma x or S, scatter matrix of x, samples x has eigenvalues lambda 1, lambda 2, and lambda 3. Again, let it be a 3 dimensional samples features. Let this be 50, let this be 20, and let this be 2. in this case, how much information should we, so if you want to retain 90% of information, if we consider only first eigenvalue for only one eigenvalue for E1, so we have 50 by 72, and which is close to 69%, 70%. So to retain 90% of information, at least we should consider two eigenvalues. Information in considering E1 and E2 together is equal to 70 by 72. This is greater than 90%. Okay, so you should consider now two dimensions to project. So in this case, you should consider, okay, you should consider two dimensions to project. Okay, to retain 90% of information. Whereas here, to retain 90% of information, one dimension is good enough. Okay, so that's how we decide on the number of directions or the dimensions to which the data samples has to be projected in principal component analysis. See, this principal component analysis has applications not only for dimensionality reduction, it also has good applications in few and in fact several other image processing applications. See, for example, if you have an aeroplane, okay, our objective is to classify the aeroplanes. Okay, assume that this is an aeroplane. Okay, and we have samples wherein one aeroplane is imaged like this, another aeroplane is imaged like this. Okay. Okay, another aeroplane is imaged in arbitrary manners. Okay, so now given this, what we want to do is we want to do classification. Say there are some aeroplanes first, and then there are some cars. So cars are also probably imaged in different directions. Okay, so one car is like this, and then another car is taken like this. And so on. Okay, so the images are not very well aligned. In this case, if I ask you to classify the aeroplanes versus trucks or whatever, what is the first step? First step is to align all these images in a particular direction. Because if you want to extract features or do classification, first step is to align them. So to align them, we need to know what is the dominant direction of this data sample. Okay, so these are the dominant directions. Similarly, these are the dominant directions. Okay, of the cars and the trucks and so on. So how do we find out the dominant direction? Dominant direction, see, we can find again using principal component analysis. How do we do it? Say, assume that in the region where the aeroplane is there, all this be, okay, foreground. Okay, and the region where the aeroplane is not there, let that be background. Okay, so in such case, what do we do? This is all, say for example, we represent the foreground pixels and background pixels. So let us take the XY locations of the foreground pixels. Okay, so you can take XY locations of the foreground pixels, each of the foreground pixels. Now, if we consider these as the foreground data samples, what do you see here? The data samples are spread in a particular direction, and hence you can find out the dominant direction of the data, and you can realign that horizontal or in the direction of your interest, right? Similarly here, if you consider these are the foreground samples, okay, each of the pixels in the foreground are, okay, the coordinates of the foreground pixels we consider as the foreground samples itself. Assume that the samples are represented in 2 dimensions. Okay, let the dimensions be either you can consider this or you can consider this itself. Okay, X and Y. Okay, now you each of the consider X. Oh, XK comma YK. Okay, of foreground pixels. Okay, where K equal to 1 to n samples if we have in foreground, these will form the features. And the covariance matrix with that, it will be 2 cross 2 covariance matrix. And this will help us, okay, essentially this will help us to find out lambda 1 and lambda 2. Okay, and then E1 comma E2, and essentially E1 will be like this. This is E1. Okay, so and hence using this E1, you can, this is the direction, dominant direction of the object. In other words, object is oriented in the direction, gives orientation of the object. Okay, so it gives the orientation theta of the object. Okay, and hence you can realign as pre-processing for feature extraction and classification. Okay, this is one of the potential applications where the PCA is used. Identification of orientation of the object. Objects. Okay. So likewise, there are several other applications. One is dimensional detection, and other is the orientation detection, and other is compression of the data. As I said, if we compress the data, the information can be compactly represented in terms of the principal components, wherein there is a lot of data saving, as we discussed before, from ND values to N plus D values, you can use for representing the same data samples if you project onto one dimension. Right? Thank you.